Good afternoon. My name is Harald Haas. I am the Van Eck Professor of Engineering at the University of Cambridge. And as you have seen, Cambridge is a very proud member of the Connected Festival, Futures Connected Festival. And what we are going to show today here in Cambridge, the way we participate, is by showing you a number of experiments we do as part of our research and our research innovation. We also have our partners here in the lab, the University of Bristol, the Smart Internet Lab with a demo on holographic living. We also have our partner Pure Li-Fi here, which shows a little bit of future telecoms technologies around Li-Fi, something we introduced 2011. So, as I said, my name is Harald Haas. I'm also the director of a national telecoms hub on network of networks. It's Titan. We also lead some of the activities within the futures, the Federated Telecoms Hubs, FDH, on commercialization, standardization, as well as skills development. So coming back to Titan, so really what we do in Titan as a hub, we really bring together different network elements from non-terrestrial networks, so connecting satellites and satellites connections to the ground. We also connect aerial platforms, drones, hubs, and other devices with new communications technologies, with new protocols. And that is a big element of the Titan hub, so terrestrial, non-terrestrial. We also work in bringing together the classic fiber networks, and you've seen from colleagues in Southampton the opportunities that hollow-core fibers will bring to the fore, and something we exploit as part of the integrated network of networks, in addition to expanding networks terrestrially with new RF technologies. Bruno Clark's mentioned to you RSM. We heard about the cell-free massive MIMO in Belfast. And these are all new innovations we bring into that mix of networks. And lastly, optical wireless communications is part of the networks as well, because we also look into networks expansion beyond terrestrial and going underwater as well, which is an element that has traction as well. As we heard in the panel, defense applications will be becoming more and more part of our fabric of networks. So this is a brief summary in terms of what we do. Now I would like to put a little bit of a spotlight on the various demos we have prepared here at the Li-Fi Research and Development Center lab. So one of our demonstrations here is with our partner Bristol, the Smart Internet Lab, a joint work that involves multiple cameras that take pictures of a person and build a holographic object that will be able to live in the metaverse, in the cyber world. And we are connecting that hologram to Bristol, and together we then have the two people meet in the cyber world, so that in the future a Zoom call is not on a two-dimensional display. A Zoom call could be in a real environment, mirrored into the cyber world, and get new experiences, the fully immersive experience. To this end, I should also say that we are part of the Joiner networks and very proudly be part of the Joiner network. We have an entire Joiner node that you see in the background here in the lab, which is fully equipped with all network layers from switches to cloud. And we also have new 5G new radios installed in the lab to be able to connect these cameras that you see later on. And in addition to that, we are one of the few sites that have a satellite dish at the top of the roof. So we have NTN connections to LEO satellites as well. So we have all the elements of a network of networks available in the lab. So if I now go further and introduce you to our colleagues from Bristol that will tell you a little bit about that really unique and forward-looking application of the cyber-physical continuum, the metaverse, the holographic human, we call it, is something that you see here with an installation. I'll hand over to you.
Thanks, guys. So hi there. So what we have here is a real-life application. So we use the latest in hardware and software. And in essence, it's as my colleague said, we're trying to capture the person you see there and create a 3D model out of it. So this is something that is already being done, but what is special here is that first of all, it's very portable. So we combine Wi-Fi with Li-Fi. We use multipath TCP, which means you can use multiple channels to send the same data. So we can increase the bandwidth as much as we need, right? So another special thing with this is that we use a new technique called Gaussian splatting, which means that in video games usually you have like just a 3D polygon, right? So you can kind of tell that this is fake and it's not a real image of a person or a character. Here it's very photorealistic, and although it's a 3D model, you can move around and you can see different angles of the same object or the same scene, and it just looks like another photo, right? So yeah, so now we're capturing this person. It will show up here in a bit. But at this setup, we have a lower FPS because we don't really need anything higher. But we have used it to capture video, for example, so we can hit up to 30 FPS. So you could, although here we're just capturing a static person, you could capture like a scene where you have movement and all these kind of things, and you can create a video that is using the same technology. So you can use it for training, for example. So imagine you have medical students and you want to train them on a surgery. You can have in the surgery room, you can have something similar setup like pods around the environment, and you can capture the surgery, and then you can show this later on when you want to train them. They can move around and they can see different aspects of the same thing, where it's very important to have photorealism, right? And as I said, this is very portable. So as we see here now, this is done. So we can see the person here has been rendered. And then we have another person which is in Bristol actually. So we're using the joiner network to combine these two 3D models. And then we have the environment that is also from a totally separate place. It's in Bath. And we capture this environment ahead of time. So we took one of the pods, we went there with a battery. So it was all portable using Wi-Fi and the Li-Fi. And then now we can just combine from different areas in UK. We just create in the cyberspace this newly rendered representation. So yeah, so this can be used in many different areas, and there's so many applications. So yeah.
That's wonderful. This is a good example of really an innovative applications that we might be seeing in 2030 and beyond. Holographic displays, holographic immersive participation in a cyber world. A very good example, it uses, in order to render the three-dimensional object, it uses AI, as we just heard, and it also involves a lot of new technologies that you see with an array of 48 cameras around here, and these 48 cameras, they are at the moment connected wirelessly, and you can imagine this is a hugely dense environment where a lot of transmitters need to emit data in the uplink, and this is really creating a challenge to the radio spectrum. And Simon Saunders very nicely introduced spectrum as oxygen. But here, there's many users that occupy a lot of oxygen at the same space. And this is where the challenge comes with the classic RF spectrum. It's the dense use of it, and also the availability and data rates that we require if we want to stream data at really high speeds, sort of really not compress data in order to avoid loss of quality. Then we need more spectrum, we need more data rate, and that's why here in the lab in Cambridge, and we've been working a lot, as others have done as well, on using the optical spectrum, which is the infrared, the visible light, and also the UV light, to really enhance and create new applications, and that's why I'm really also proud that I spun out 13 years ago a company in Scotland, in Edinburgh, Pure Li-Fi, and Pure Li-Fi has been on the forefront of optical wireless communications on Li-Fi commercialization, and it's a good example how fundamental research, so we fed in a number of fundamental IP at the beginning of Pure Li-Fi, and how they took that on and created products and really innovated further. But not only that, Pure Li-Fi has also been leading a standard, not a general standard, a really important standard within the IEEE 802.11 family, which is the classic Wi-Fi family, a standard with a reference BB. And as we speak, people now and companies like Pure Li-Fi and others work on a new release of that standard that would allow new capabilities to come in. So with this little preface, I'd like to hand over to my colleague, Bart Bowser, who is the VP of Commercialization and Sales, and he will talk us through some of the really exciting products that Pure Li-Fi is offering to the market, and also will explain to you a little bit that how the light spectrum and the radio spectrum can help each other. And that is through, for example, sending visible light or infrared light through a window to enhance coverage, 5G coverage indoors, because we need to realize that 80 to 90% of all traffic originates and terminates indoors, and there's a problem. And I think what, in that context, I wanted to introduce as well, we have heard about a number of figure of merits in the use of spectrum, energy efficiency, spectrum efficiency, but there should also be a figure of merit, in my view, in terms of usefulness per hertz bandwidth. Because in some sense, the question is it useful to have a high power transmitter somewhere and force the radio waves through a very strong blocker like a window? Is there a better way to use the RF spectrum outdoors and indoors and basically bridge the gaps in between? And this is really where Pure Li-Fi has pioneered a number of products. Bart, over to you.
Thanks, Harold. So, as Harold said, Pure Li-Fi has essentially been around since 2012, and it was a spin-out from Edinburgh University. But in the early years, we were very much a deep tech organization, very much focused in the military and in the intelligence space, building bespoke solutions for both frontline environments and secure locations, premises. Back in 2023, as we know, 802.11bb standardization of both Li-Fi and Wi-Fi meant that it became completely interoperable without dropping a session. And this got us start to think of many other applications that we could actually build from a Li-Fi perspective. But applications that potentially can address some of the challenges consumers may face in their home, people may face in the enterprise world, in buildings, but also the carriers themselves, the network operators, the services that they want to deliver. We know that attenuation is very high when it comes to 5G penetration into a building. But it's not just 5G, it could be 6G, it could be millimeter wave, and again, those attenuations are even greater. So we started to look at some of the solutions that the carriers are trying to deliver and see how we could address some of the challenges they face, as well as the consumers and the enterprise. And one of those is around fixed wireless access. Traditionally, the modem has been inside the house, and therefore the performance hasn't been great. It has a number of impacts to a carrier. One, they have to generate more power to get a signal through, but even after they've done that, still the bandwidth is less than it could be if the modem was moved outside. So the carriers then started to look at fixed wireless access, putting a modem outside the building fabric, but still had the same challenges. The challenges of having to drill through walls, having to get permissions to do so, having Faraday cages, glass type environments, all of which create endless problems to that. Clearly the consumers and clearly the enterprise customers were all suffering at the same time. But the carriers realized that if they did that, then they could optimize their network as long as they could find a solution for getting that signal still into the building. So talking to some of the carriers, talking to some of the CPE vendors, Pure Li-Fi developed a solution which we call Links Bridge. And Links Bridge is essentially using the glass of a building to actually transmit the data from outside to inside and vice versa. And this is a demonstration that we're going to show to you today. So as we look at the display here, we have a window. It's a double glazed window. It's an AG2 energy efficient window. So one of the challenges we first noticed is there are so many different types of windows. We need to have a solution that can calibrate itself when it attaches to that glass. So the Links Bridge solution that you see here can work from a single pane 5mm all the way up to a triple pane 30mm window. It can also work with the energy efficient windows, so the AG1, AG2, AG3 windows, all of which have different grades of silver coating in between, again representing a further challenge. So our solution has that auto calibration capability, which is one of the first things. But before we get into the actual device, let's look at the overall setup that we have here. So this is, you could say, your traditional home working environment. So on this side of the window, we're inside the building. We have a laptop here, which would normally be, I suppose, wirelessly connected to a router, which in turn would be connected to the internal Links Bridge units. For the purposes of today, we have connected the laptop directly to the Links Bridge just to avoid too much cabling. But essentially, the internal Links Bridge plug has two functions. Function number one is, because it's connected via DC internally, it's also working with our partners. We've managed to create solace. We've managed to create the ability to wirelessly charge the external unit through the glass. Now the external unit only needs about 5 watts or so. So we can actually generate more power than that. So what better way to use that additional power than to actually deliver power over Ethernet connectivity from the external unit to what would be your traditional fixed wireless access modem, which would be on the outside of the wall. Again, addressing a challenge that a carrier has. Not only does the carrier now use data through Links Bridge, but we're also providing power, so no need for any more drilling or any more permissions associated to that. And therefore it becomes, to a certain extent, a self-installation capability. Again, reducing costs for carriers in terms of having the truck roll to visit each location. If you can send a solution through to a consumer for them to self-install, so much money can be saved, faster time to revenue. But the actual solution itself, so as I say, you've got an internal puck unit here and an external unit. Between the two of them, you have a 1 gigabit bidirectional link, symmetrical, creating a bridge through the glass. And as I say, you've got the power also going through that. And that's the light antennas in each of the puck units that are communicating to deliver that bridge. On the outside, you have obviously the external unit, and as I mentioned, you've got power over Ethernet, which is would be delivered to your external modem. In this case, again, for the purposes of the demo, we've just connected it to a small media server, so we can show both the speed and we can show some media on the device. So that's the basic setup of the solution. If we come over here to the laptop, the first thing that we're going to do is to run a test of the speed between these two units. Okay, so Ethernet here, Li-Fi in the middle here. So we're going to run a test of that, particularly of that link. We give it a moment, and as you can see, just shy of a gigabit in terms of the link between these two units. But I suppose to make it more meaningful for a consumer or somebody working in their office, it might be worth looking at some actual media itself. So again, taking media from this media server, Ethernet, Wi-Fi, and Ethernet again, we're going to play a video. And as you can see, already playing. But I suppose the real test is when you start to move that video forward to see how good is the buffering. It's almost immediate. So it's showing you that not only do you have the gigabit link there, but actually in a real environment it's actually playing data from outside. Just coming back to the two units, a lot of people ask questions about, well, how do they attach to the glass? We actually use a tape that's called gecko tape. It's actually designed on the nanostructures of a gecko's foot. It's been widely tested over many years in many different climatic environments, and it can be removed and put back, and in the case it gets dirty, it can just be wiped clean. I should also point out the external unit is also IP rated as well to be outside. So that is the Lynx solution. I would say that where we are now is very close to commercialization. We're in final trials with a number of the major carriers in the US and also here in Europe, also working with ISPs and CPE manufacturers as well as we start to think what's next. We can already deliver this capability. We can already see that it's self-installable. The carriers clearly see the benefits of this in terms of the network optimization and the cost savings, and the consumers themselves can clearly see greater speeds from an experience point of view versus having the modem inside. Okay, so let's move on. The second solution I wanted to talk about was the Cube. For all intents and purposes, this is a mobile hotspot or access point. It has Ethernet connectivity in the back and power to connect to an internal router, and it can be positioned in a multitude of different locations, on a desk for a home worker wanting to work in a secure environment, in an office, in a particular room, for instance, where they want to have secure Wi-Fi rather than Wi-Fi access, or even on a shelf on the ceiling, as an example, where they want a broader cone of coverage. I'm talking of the coverage, it covers about 60 degrees in angle. It can deliver about 3 to 5 meters square in terms of coverage, so plenty of coverage across a desk or a larger desk anyway. And it can support up to 8 clients as well, sitting and accessing the solution. We see many use cases for this. Originally, this was something that we started to think about from, as I say, the military and intelligence perspective. But now we see a lot of use cases within the financial sector, as an example, or within the government environments where they do have secure locations, or they do need people to work very securely with very low latency and very high speed, with no contention. But also we see it in environments which are probably quite new. So when you start to think of virtual reality, you start to think about gaming and how big gaming is getting. Nobody wants to have any of the slowness associated to possibly RF. They want real time, they want an immersive experience. So low latency is absolutely critical to them. So in the gaming industry, it could be used, if you can imagine, with the Google or the Microsoft lenses that they have. In addition to that, you've also got training. Again, this solution could be used in a training environment, in a virtual reality experience that the trainer can go through from a learning point of view. So that's the Cube at that end, but you clearly need to be able to connect it to something. So what I have here is a mobile device, mobile phone, and if I switch it on, you can see we have the light antenna module on the device there. So that will now connect with the cube access point over there. But of course you move around with the device, so you may not necessarily have that pointing directly at the cube. So we've also added an additional antenna at the top as well, so it gives you the ability for the device to move and it will still be connected. Furthermore, we've also got a laptop where we've built the light antenna module into the top of the laptop, as you can see here. Again, the same principle. You could work in that sort of office-based environment with immediate connectivity between the laptop and the cube. And it could actually be done through USB and dongle as another option. Currently we're working very closely with a number of the CPE vendors for mobile devices and for laptops now, and ultimately the goal will be to potentially have the light antenna module actually built in to these devices. So it just becomes an additional an additional network that the consumer can access in a Wi-Fi environment. Harold, that's it for me.
That's excellent. Thank you, Bart. And that was a classic example of how university research from low TRL level can be taken to TRL level 9, really which is now deployed and used in the defense sector, for example, to a large scale, because there's one key property of light. It is more secure on a physical layer because it doesn't penetrate through opaque objects like walls. So, thank you. So the vision that we have really is connecting everything with everything, building the ultimate nervous system of a really modern society. And there's many more use cases where we need better connectivity. Mentioned the non-terrestrial networks for satellite links, bringing satellite links into the fore. But we also have applications underground that require much higher capacity on a on a link basis, so more data rates. And a few years back, as part of an EPSRC funded project, TAUS, we've been asked by the BBC that use really high-end cameras, obviously, to see whether there's a solution to connect a high-definition camera in a studio, and the studio was Strictly Come Dancing, which is a very popular show program in the UK, to wirelessly to the control center. At the moment, they use fibers to connect cameras for really uncompressed, high-speed data flows back to the control center. And radio communications technology isn't available at speeds of 10 gigabit and beyond. But that wasn't really the main problem. Another problem is the latency. You want to have really low latency data links in order to allow sort of immediate actions if you want. So that's why we've been working over the years of developing optical wireless communication solutions to connect those high-speed cameras. And I'm delighted that I can now show you an experiment where we have used a standard digital output of a camera, of a high-definition camera, and have transmitted that signal over a distance wirelessly to a monitor at a really uncompressed way in really high-speed fashion. And I'd like to hand over to Hossein, who is giving us a bit more details of that demonstration. Thank you.
Thank you. So this experiment demonstrates real-time transmission of high bandwidth SDI signals over an optical wireless link. SDI using off-the-shelf devices. So SDI stands for Serial Digital Interface, a family of digital interfaces that was first standardized in 1989 by the Society of Motion Pictures and Television Engineers. For live streaming of uncompressed and unencrypted digital video signals within television facilities. There are various SDI standards to support different video formats and bit rates, including, for example, standard definition SDI, high definition SDI, and 12G SDI, which is also known as 4K ultra high definition or UHD video. So since these SDI interfaces, these standard SDI interfaces are available in professional video equipment with coaxial connection ports, they can be used to connect different pieces of equipment, including recorders, monitors, PCs, vision mixers, and more. In this experiment, as an alternative to cable connections, we propose a wireless solution based on low cost and low power laser-based optical wireless communications using vertical cavity surface emitting lasers or VCSELs. So this current setup demonstrates live video streaming from a 3G SDI camera through this optical wireless link, and it's cast on this Full HD monitor here. And the bitrate currently is set at 3 gigabit per second with this 3G SDI signal interface. As we can see from the eye diagram on the oscilloscope, the proposed setup achieves a very high quality factor, indicating that it's operating at very extremely low bit error rate performance. So the link setup, let me just explain a little bit more about how this link works. The link setup is composed of an optical wireless transmitter and an optical wireless receiver. So at the transmitter side, we use the 3G SDI data stream generated by the camera here, and we use this signal and we feed it into this VCSEL device here, which operates at an output optical power of about 5 milliwatts, and it uses 940 nanometer infrared wavelengths, which is not visible to human eye, but the link is established already. And at the receiver side, the received optical beam is focused onto this high-speed photodetector, and then we use a commercial SDI equalizer here in order to compensate for any channel impairments that can cause signal amplitude distortions. And then we take the output signal here and we use an SDI to HDMI converter to convert it to HDMI that can be displayed using an HDMI cable on this Full HD monitor. So basically, this is the setup. And as a result, as you can see, the live video is transmitted in real time without any intermediate processing stages in order to avoid latency. And this link has a latency of about 20 nanoseconds, while real-time video streaming with ultra-low latency requires a latency in milliseconds, which basically showcases that it provides an excellent performance. So the future possible applications of this setup, it can be thought of considering the appealing advantages of VCSELs in that they provide very low power consumption, along with their very high bandwidth and also very well controlled output beam profile. In the future, by integrating VCSEL-based transmitters and receivers into video equipment, the video production industry will have an option to replace the existing cables by using this optical wireless link, and therefore we can provide a fiber-grade performance with the flexibility of wireless connections. And considering, so we can also manufacture the required transmitter and receiver subsystems, but to provide auxiliary optical wireless connections by reusing the existing SDI video equipment without modifying them. So what makes this demo unique is that this demonstrator for the first time showcases live HD video streaming via an optical wireless link operating at ultra high speed and low latency by using off-the-shelf component. The key features of this demo that makes it unique are low power, error-free, ultra low latency, and ultra high speed. These key features address the key performance requirements of future 6G communication networks in terms of energy efficiency, reliability, data rate, and latency. And considering that there is an array of commercial and commercial components already available for video signal acquisition and conversion, this provides a unique opportunity to introduce a cost-efficient and high-performance optical wireless solution for next-generation SDI connectivity in 6G networks. Thank you very much.
That's great, Hossein. Thank you very much for that very nice introduction about the technology. I want to add 2 comments about that. The first comment is that we use lasers that are already in mass market products in your smartphones. When you have face recognition, you have a red laser that scans your face. That is a vertical cavity surface emitting laser, a VCSEL that we have been using there. So they are already in our devices, so it's commercially available. The second comment I wanted to make is, while we have shown here a link over 3 meters or 4 meters or so, the link distance can be substantially increased into thousands of kilometers. Starlink at the moment, to build their sort of network of LEO satellites, they use optical wireless communications technology for inter-satellite communication. So this is a blueprint of a technology that could go into space, and also from space to ground. That's why we really are excited about the fundamentals of developments on laser-based optical wireless connectivity. I would like to move on a little bit. We talked about spectrum and we talked about sort of the RF spectrum, but the electromagnetic spectrum includes, as I said, the optical wireless domain as well. And the optical wireless spectrum is 2,600 times larger than the entire radio spectrum. I mean, really, the entire radio spectrum from 0 to 300 gigahertz. Multiply that by 2,600. You have the spectrum available in the optical domain. And that spectrum is unregulated. It's free to use anywhere. You don't have to ask for it. You don't have to pay for it. You can use it, and that's what we have done here in the lab. And we have devices. We have really high-speed devices and commercial devices. And I want to now move to another commercially available device that is available, and that is laser light. You all know the white LED light bulb, which is around, founded by Professor Nakamura. Suchi Nakamura got the Nobel Prize for it in 2014 for the blue LED, which is the basis for white light. But also he has founded a company in Santa Barbara. It's called Kyocera SLD Laser, so acquired by the Japanese company Kyocera. And they produce really, really powerful white light sources based on a blue laser instead of a blue LED. And that provides higher brightness, it provides higher bandwidth as well. And we have been lucky enough to collaborate with them for the last 10 years or so. And have been using some of their devices to build what we call wavelength division multiplexing systems. So because of that huge spectrum available, we can chop it up into little sort of bins, and every spectral bin is its own data channel, if you want. And we have created a system. If we move over here, we have created a system with these commercially off-the-shelf available laser light devices that are sitting in these boxes here. You don't see the light because the light coming out of that laser inside, and it's coupled into a piece of fiber. This is plastic optical fiber, and the fibers are sort of coming together here at the center part of what we call an optical access point. So there's white light coming out, as you see here, a very bright spot. So there's light transmitted, and with this light, with 10 channels, and these 10 channels on average cover or carry 10 gigabit per second. In a full-blown operation, this system is able to transmit 100 gigabit per second wirelessly, and we've shown that at the consumer show in Las Vegas, CES 2022. We've shown it at various conferences. And this is really a pathway towards what we see the terabit wireless world. And we need a terabit wireless world. If you look at cyber physical continuum, if you see the application from our colleagues in Bristol, if you want to connect all these many devices at high speeds, at high refresh rates, then you need a terabit per second wireless link. And that's a requirement. You would need to have in the RF spectrum 100 gigabit per second channel, and that with a spectrum efficiency of 10 bits per hertz of 100 gigahertz. You can readily imagine that is probably not going to happen. So future-proofing wireless communications into the terabit per second wireless world has to be optical. The other point I wanted to make at this point, which we haven't talked about, is quantum networking. Quantum with quantum key distribution through fibers already shown, also in sort of satellite networks. But really having end-to-end quantum secure communications, you have to have everything in between optical. And that is another key advantage or a key motivator for us to look into all optical networks. And I would like to hand over now to my colleague Hossein, who will talk you through the setup here a bit in more detail.
Thank you. So, hi. So in this demo, we actually demonstrate the capability of a Wi-Fi communication system using laser-based sources in surface-mounted devices. And we also implement wavelength division multiplexing to enable 10 parallel channels and achieve over 100 gigabit per second. So in this demo, we just enable activate 4 channels, so we could achieve over 40 gigabit per second, as we can see here in this monitor. So I will just explain briefly the structure of this SMD device. So here in this package, we have two laser mounted in the surface of the package, and we have a phosphor reflector in the center of the package. Here, the structure or the orientation of these laser diodes inside the package are oriented in such a way so that the light emitted from the lasers incident to the phosphor reflector, and a part of this light is reflected and coupled into an optical fiber attached here to this optic system to transmit our signal in wireless channels. And here, before moving to the receiver side, I would like to just mention that one of these two laser diodes emit blue light, and when the blue light incident to the phosphor reflector, part of this light exit the phosphor materials emitting a yellow light, and the combination of yellow and blue light can form the white emission, as we can see here in this one. And one important point here is this: for this SMD device, it's not only diffuse the light incident to the phosphor reflector, but also convert the coherent light to non-coherent light. And actually, this is very important for eye safety consideration and illumination performance. The second laser source here in this SMD package emits a light with a different wavelength, and this is for data communication or communication purposes. For example, if we would like to implement a wavelength division multiplexing with multiple channels, we need to use laser diodes of different materials so that we can enable multiple wavelengths for data communications. Yeah, I will move forward to the receiver side. We have here, after we coupled our reflected light to the optical fiber and transmitted from this optics to the receiver, we use here a photodiode array with filters to reduce the crosstalk and also to enhance the performance. We attach this receiver to multiple channel scopes to digitize the received signals and then going to the processing phase. And in data processing here, we use our laptop with adaptive algorithm here. And this adaptive algorithm actually monitor each channels and assess factors like signal strength, noise levels, and interference. And based on that, the algorithm dynamically adjusts the number of bits allocated to each channel so that we can maximize the data rate while ensuring the target bit or rate achieved. So in summary, or in other words, we can say that the channels with better condition can carry more bits, but those with poorer conditions have fewer bits allocated. With this way, as I mentioned, we can achieve higher data rate, as we can see here. With only 4 channels, we have over 40 gigabit per second And for the full system, as the Professor has mentioned earlier, with 10 channels, we are able to achieve over 100 gigabit per second. Such ultra-high-speed data communications can open wide range of real-world applications. Actually, when we talk about this Wi-Fi system, we talk about a secure, ultra-high-speed, and also efficient communication system. Here, we talk about applications like smart cities and intelligent transportation system. The Wi-Fi system here can enable high wireless communication data rate between vehicles and from the infrastructures to vehicles. And this is actually one step to enable efficient autonomous driving. Another application for this Wi-Fi system actually is in free space and even in deep space optical communications, where higher data rate can be transferred between ground stations and satellite stations. Another era of applications for this system actually underwater, because such kind of Wi-Fi system can enable efficient and high accurate navigation underwater, and also can enable the communication between underwater and even drones outside or an outdoor environment. One of ideal applications of our Wi-Fi system is in-home networking, achieving high data rate and high data rates inside home, enabling internet access for all users inside homes and smart buildings. So thank you.
Thank you, Hossein. That's a very nice introduction, and I'm glad you mentioned the use cases for underwater communications and also drones. And it's very important if we move into three-dimensional channel modeling and three-dimensional communications with terrestrial, drones, aerial platform, and satellites. There's a whole raft of new challenges on how to manage the spectrum in this sort of three-dimensional space. And it's really prudent and important to allow radiation that's confined. So you really illuminate what you want to illuminate and not everything beyond, because that is interference. And I just wanted to give you an example how optical spectrum can allow this by the properties of light. These are the 4 receivers that you see on this communication system that are each receiving with a different filter, 10 gigabit per second, but they are not at the same location. They are spaced apart, and despite that, we have no interference. So we are able to direct 4 channels from a central point, from a point to multi-point, and this is what we call in wireless communications multi-user access. So we basically have, this could be your smartwatch, this could be a drone, so we are able to manage the different spectral components in an intelligent way. And that, by the way, is also part of our mission as the wider joiner infrastructure here with the radio systems you have mentioned. We have the optical wireless systems now here, and now we develop AI algorithms to intelligently manage all these different air interfaces in order to create a best performing experience to the user. And that is a really complex problem, and the more spectrum we have, the better we can, the easier is to find a solution. So essentially, we're targeting an environment where we get sort of a gigabit per square per cubic centimeter, really high density wireless connectivity. And now if you imagine you have so many sensors around here, so many detectors, it's every receiver here is a sensor, right? As such, we can gather a lot of data of received signals, and every transmitted signal carries a signature of the environment via the channel. So we create a rich scanning environment, a sensing environment, and again, that feeds into the mission and vision of beyond 5G. Some people call it 6G, but beyond 5G, where joint sensing and communications is a crucial part of a 6G standardization going forward. So really, these are fundamental blueprints that really enrich future telecom networks now with pure Wi-Fi, but also by 2030 and beyond. And there's one area, one experiment I'm really passionate about, super passionate about, is looking at energy harvesting. And Professor Petriopoulos in Southampton mentioned to you how holocaust fibers can be at the same time used to transmit a lot of power through the holocaust fiber. We have that already in a real world with the advent or with the use of solar panels. Solar panels are part of our sustainable mix of energies that we need to have. But solar panels are also photonic detectors because they convert a photon energy into electrical energy. That's the process. Now imagine if these photons that come into a solar panel are not only sunlight, which is a constant stream of light, but they are coming from our data encoded light sources with a fluctuation of the photon sort of flux, the net density of photons coming in. And now that creates a different signal at the output of a solar panel. So a solar panel in principle, and that's been shown 10 years in a TED talk I gave, are high-speed data detectors. And that's something we have patented. We have created with prototypes. We have installed it at the far out island of Orkney, and the Orkney in the UK, which is one of the most deprived wireless data and connectivity environments, where people still live on 2 megabit per second data lines from a copper cable. And we've installed a technology on an island called Grahamsey, on a lighthouse called Hoy Lighthouse, and have provided 10 megabit per second to 2 homes 100 meters away that couldn't really operate a high definition TV with 2 megabit per second. So we helped them in a trial 3 months long, and to showcase the robustness of the technology to ambient and turbulences and atmospheric conditions. So solar panels, like LEDs, are a crucial element for us in the communications world. And I'd like to hand over to Rizwana and Northman to show you what we have here in terms of that demonstrator.
Hello everyone. So today we are showing you a real demonstration of an optical link that utilizes the solar cell as an off-the-shelf solar cell, a normal solar cell that exists in the houses at the moment, and to offer you a sustainable solution for energy as well as for communication. So what you can see here, we have an optical link for over a few meters, around 10 meters, that in one side and in another side of the room. So maybe we'll point it out that. So you can see now is the link is inset optically with the two solar cell at the transmitter receiver as well as the transmitters. And what we are showing you here is a video that's been streamed from the other end into the system in here. And you can see with a high quality, basically video streaming, and we are transmitting the signal. And here is basically the data rate and the signal, the throughput of the signal over time streaming. And if we are looking into the light coming out of the transmitted modules, you can see that we have a camera now trying to point out in the system, and if we are trying to block that signal, maybe if you point it out in here, you can see that the signal is blocked, and you can see the data rate is no longer, the request is timeout, and you can see that the light beam in here is the transmitted we are using. So now if we look deeper into the transmitter module that we created, and you have a transparent version of that transmitter, you can see here is basically 3 main units. Is the signal that being fed from any devices, smartphones or telecom devices or laptops, that fed into a system with a processor to process the data and hand over to basically a driver circuitry that we designed to drive the signal and take that the electrical signal and shine it into the optical space optically, and then receive that using the solar cell. So if you think of application-wise for these solutions, imagine in a remote areas that are 60% of areas around the globe are not connected at the moment. And this solution where you have this rural area where fiber optics maybe cannot reach or cannot be set up in the mountains in area and a deprived area where it's hardly having access to this device, to wireless and RF solution, this handy device could be portable, could be easily installed without having to having to suffer the difficulty of installing this power station and so on. And that is one of the main solution we are offering. And I'm hand over maybe Rizwana if you want to say
Yeah,
something.
so one of the advantages of this system as providing the connectivity to underserved area is that the installation for the system is very easy. You don't need a technical expertise for installing the system because it is not highly dependent on the alignment. You have a larger receiver area, so you don't need precise alignment, which again makes the system very affordable. So you have a simplified installation, affordable system, and it also provides you, it basically reuses the infrastructure that is being deployed in underserved areas, like for solar harvesting. A lot of areas in India, in Africa that are not well connected with the network are actually deploying solar panels for energy harvesting. So in those areas, it's possible to leverage that infrastructure of solar panels for establishing the communication link. The other possible application of this system could be satellite to satellite communication. Satellites have huge solar panels installed in them already, so you can use those solar panels for communication, and that can provide you with the basic control communication, establish the link between the satellites, and once that link is stable, you can do the communication on top of it with better alignment and everything. Yeah, and that's about it. I'll hand over to Harald. Yep, thank you.
That's great. Thank you, Rizwana, and thank you, Othman. I think we are coming at the end of our hour. But I hope we have given you a little bit of an impression of the kind of sort of research, advanced research we do, but also where we are in the real world now with the products Pure Li-Fi has done. And all of this is part of the joiner fabric. So we connect to the joiner node, through the joiner node to our sort of 9, 10 partner universities. And this is essentially an invitation for coming to us, collaborating on the network we have here, the wireless network with Joiner, to do some joint experimentation for 6G trials and beyond. And with that, I'm coming to the end. I just wanted to say that we wish to be physically in Bristol right now. We are part here as a satellite. My vision and hope is in 2030, maybe before, beyond, that we can participate in the cyber world like in the real world, being part with you while we are here, and also have a toast with all of you at the end in the cyber world. Let's see how we make this happen. Thank you very much, everybody, for joining us today, and thanks everybody for the demonstrations. I wish you a great rest of your days. Enjoy it.